Okay, hello everybody. So my name is Qusaichemistrytutor, and today we're going to be talking about carboxylic acid derivatives and um, their reactions. So this is actually a problem that I encountered in the tutorial that I TA for Organic Chemistry 2, but I did take the problem and tweak it a little bit so that it's actually more difficult, so that we can have a more in-depth discussion. So the first step with this type of problem is to figure out what's your electrophile and what's your nucleophile, right? So what we're going to do is, usually it's easy to figure out your electrophile in these cases, right? It's going to be one of the carbons here because they have a slightly positive charge, and that's because this oxygen has a slightly negative charge. It's really electronegative. It's an sp2 oxygen, so it's more electronegative than usual. So most of the electron density will be close to that oxygen. So the electrophile will be one of these carbons. Now the nucleophile, it's a little bit more difficult, right? So the way I see it is, for the first step, we have, that's a bad pyridine. Okay, so maybe that way. Okay, that's still a bad pyridine, but slightly better. Okay, the way I see it is that we have three options, right? So we have this nitrogen, right? That's option number one. We have the oxygen here. That's option number two for our nucleophile, and we have the nitrogen in the pyridine, which is option number three. So how do we figure this out? Well, let's look at this nitrogen first. This nitrogen, the lone, usually lone electron, because nitrogen is more electropositive than oxygen, it's usually more willing to donate its electrons, so it acts as a better nucleophile. However, in this case, the lone pairs of electrons on the nitrogen actually occupy that p orbital, right? And they're actually involved in the aromatic system. And as we know, aromatic systems are really stable and they're really hard to break. And if these electrons attack the carbon, then they're going to break the aromatic system, right? And that's not thermodynamically stable. So this nitrogen will probably not act as a nucleophile. Let's go to the nitrogen on the pyridine as the next step. Well, the electron pairs on the nitrogen and the pyridine are actually not involved in the aromatic system. They're in the sp2 orbitals, right? So they're actually readily available to attack. So, and let's say, for the sake of argument, that it's more electropositive than the oxygen. Well, let's see what happens when it attacks. So we're going to go there, and the electrons in the pi bond are going to go back to the oxygen, right? And we're going to end up with a complicated molecule, somewhat, that looks like this. Right? And you have a positive charge here, right? Now the issue here is what's going to leave. Well, if the lone electron pairs on the oxygen come down to reform that pi bond, and this group leaves, you still end up with this positively charged nitrogen, right? And there's no protons that you could take away from this nitrogen to make it neutral. And that's not stable, right? So that's probably not going to be a nucleophile in this case. Actually, the purpose of the pyridine in this question is to act as a sacrificial base. Let me just grab the eraser here, it will be a lot more easier. Okay, and okay, we'll leave that. Okay, so it's probably not going to be the pyridine. So the next step is actually the oxygen, right? The lone electron pairs on the oxygen are not involved in the aromatic system. Yes, it's more electronegative than the nitrogen, so it's going to hold on to its electrons a little bit more. But that's the only option that we have in this step, right? So these electrons are going to attack that carbocation, and you're going to form a really complicated molecule. Not really, but just hard to draw. Okay, so we're going to form something like this, like that. Don't forget the positive charge on the oxygen, because it's now attached to three groups. And you have this Pyrrole with that hydrogen, right? Okay, so now comes the purpose of the pyridine. So the pyridine, what it's going to do is, its first thing is it's going to pick up this not that proton, sorry. It's going to pick up the proton from the oxygen here, right? And that's going to make it a more stable, a more stable group, and it's not going to leave the tetrahedral intermediate. So what we have now is something, sorry for the bad handwriting, but something like this, right? And I'm just going to make this a little nicer. Okay, so now you have this, right? Now we're ready to break down this tetrahedral intermediate. So the electron pairs on the oxygen are going to come down. If this group leaves, we're just going to end up with the same compounds that we started with, right? And also the other thing is this group is a less stable base than this group. This acetate group is a more stable base, right? So this is going to come down, and it's going to basically break the bond between the carbon and the acetate. And so what you're going to end up with is actually something like this. So actually, I'm going to kind of reverse the compound a little bit, just so that it's easier to draw. Forgive my bond angles here. But we end up with this, and then you have this acetate group, right? Oh, my bad. Nope, that's still bad. Which is a stable base, right? And then the pyridine can react with that acetate, and like we have the protonated pyridine from the first step, right? And it can react with that acetate to basically give us the acetic acid version of this molecule, or you could just kind of filter this out of your product, right? So now we have this product. That's the end of the first step. This is the product that we have at the end of the first step, right? Now what we're going to do is a Pyrrole-Crafts alkylation, right? And the first step is to form our carbocation, right? For the electrophilic aromatic substitution. So I'm not going to go through the whole mechanism, but and if you want me to, I can make another video about Pyrrole-Crafts alkylation, but what you're going to end up with is this carbocation here, right? Now, the issue is that it's a primary carbocation, and so that's not stable. We know that secondary and tertiary carbocations are more stable than primary carbocations. So what we're going to do is we're going to end up with a hydride shift. And you're going to end up with this secondary carbocation, right? Let me just scroll down a little bit. Now we're ready to react this secondary carbocation from the reaction of that alkyl halide with the AlCl3. And so the electrons, it's going to go into the second position here. I could make a more in-depth video talking about why it would go there, but you want to look at the resonance structures, and you want to look at what has the most partially negative charge, which of these carbons has the most partially negative charge, because that's going to be the nucleophile in this case, right? So these electrons are going to come out, and they're going to attack this carbocation, and you're going to end up with, let me just draw an arrow first, something like this. Yeah, don't forget about the hydrogen here, it's going to be important in a second. You also have another hydrogen here, but this carbon now is electron deficient, so it has a positive charge. Now what's next? Well, you want to reform that aromatic system to regain the stability, right? So what's going to happen is a base, we could say a generic base in this case, is going to, doesn't have to be negatively charged, but it's going to basically pick up this proton. The electrons in the bond between the proton and the carbon are going to come down to reform the aromatic system, and you are going to end up with something, something like this. Right? So that's the end of the problem, and this is the product that we're going to end up with. Okay, so I'm probably going to go through another problem from the tutorials either today or tomorrow. But if you have any questions, feel free to email me or comment below. Also, make sure you like the video and subscribe, and click the bell icon if you want to get notifications. I'll probably also be starting doing introductory chemistry videos, so like first year chemistry. So keep an eye on that. If you know anybody in first year chemistry, let them know. But yeah, I'll see you guys later.